Right. I posted an announcement hours ago. Our tutors are set up for the semester, so we've got two individuals that are available to help you with any questions you have about class. They can help you with lab stuff. They can help you do mastering chemistry problems, or they can guide you through those. And those are Alexis and Sergio. Alexis is only available on Wednesdays. Sergio is available on Mondays, Tuesdays, and Fridays. So between the two of them, they're covering most of the days of the week. They don't encourage you if you need help, go get it. So these are no cost to you. They're in 214. That's the room right at the end of the hall as you go down the second floor. And that room's an open room, is a study room for student use. So there's no classes that meet in there. It's just a place for y'all to go. There's also a library section. There's old textbooks. So if you don't have a textbook, you can pick up. It may not be the book we're using, but it's a chemistry. There are several different general chemistry books there. And something that you can learn as a resource, if you have a topic that you're not understanding the way the author presents it, pick up a textbook by a different author and look at that same material. A lot of times it'll click if somebody else presents it to you in a different way. So that's a suggestion you use. As you take more advanced courses, you start to use things like that more frequently. Okay, we're going to continue in Chapter 11 notes and get as far as we can. The last 10 or 15 minutes, I'm going to work a few problems at the end of the chapter. So first, you get a point for just in class on time. Pretend I did that. So the first type of force that we talked about, we're talking about intermolecular forces. The first one that we introduced was the dispersion forces. It's also called London forces. And in the mastering chemistry, so the mastering chemistry assignments due tomorrow, the mastering chemistry refers to these as primarily London forces instead of dispersion forces. The next type of force we want to introduce are the dipoles. So this is for polar molecules that have a permanent dipole. So that's the reason we have to understand the stuff in chapters 9 and 10 to understand, does it have a dipole? So that has to do with the bond polarity, what's the difference in electronegativities, and then what is the three-dimensional shape? Is it symmetric or is it non-symmetric with respect to those dipoles, how they're being spread out? It also depends on the magnitude of the dipole moment. So the magnitude of the dipole moment is where we have to put all the different vectors from the dipole to add them together to find out what the total dipole moment is for that particular molecule. And these are things that are always present, and sometimes they're induced by the presence of another dipole. So whenever we have a permanent dipole, it simply adds to the attractive forces that are existing on all molecules. And whenever we add the forces, we see changes in the physical properties like the boiling point and the melting points relative to compounds that don't have dipoles. So nonpolar molecules of similar size or similar shape are not going to have a dipole. So this is an example of a compound. It's a carbon, is the charcoal colored atom. The red is the oxygen. There's a difference electronegativity in this. The shape is the dipoles. Right on top of this is moving in this direction, so this end's electronegative, this end is positive, and it's permanent based on the shape of that molecule because it's not a symmetric molecule. That means all of these molecules are going to line up in three-dimensional space so that they're oriented, that the electronegative end of the molecule is oriented to the electropositive end of a neighboring molecule. So that's kind of a stickiness or glue that holds them together a little bit. Now, when we think about the trends, and that's one of the things we want to be able to predict, we can tell something about the strength of these intermolecular forces based on the shape or the attractions that exist because of shape and separation of charge in molecules. And it's going to take more energy to pull things apart. The boiling point of a liquid is when we add enough energy to overcome the attractive forces between the particles and we separate them into individual gaseous molecules. But we're not breaking bonds, so it's not taking the amount of energy to break the covalent bonds between atoms. we're just taking and plucking them apart and let them migrate off in three-dimensional space or a gas phase. So typically, when we see a higher boiling point, that means that it's an indication of stronger intermolecular forces between comparable compounds if the boiling points are similar. Now, you can't really make an easy comparison of a molecule that weighs 30 versus one that weighs 300 because the dispersion forces are greatly different. But you can do comparisons between things that are like between 30 and 40 or 70 and 80 and look at things that are in that range. So we have to compare apples to apples in terms of they have to have at least somewhat similar similar molar masses. So another term that's used here is the term normal boiling point. Let me just go ahead and define what that means. That's the boiling point at atmospheric pressure. So when we look at the boiling points of things, we can change the pressure on something, and when we change the pressure, the boiling point and freezing point shifts as well. So whenever we refer to the term normal boiling point, that means at 1 atmosphere. So that's typically what we experience under something that's an open container. So based on what I just told you on the previous slide, answer this question. So I want to know which one of using the table that gives you boiling points, which one of these substances would have the strongest intermolecular force?
Wait, where's the ABC?
Well, okay, so I understand what you're asking. That's not. So this one's going to be A, B, C. Yeah, they're in order. Thought I'd made a neat question this morning. I forgot that part of it. Sorry. Okay, we're all in. And let's see how we voted. Everybody went with choice C, and choice C is water. And water makes sense because water's got the highest boiling point among those, and there's my ABC. Just covered up with my block. So yeah, so we look at the properties we see, and this one's a pretty clear trend. We got some that are somewhat similar, but water is by far the highest boiling point in these. When we look at things that are very negative, they have very, very weak intermolecular forces between each other in terms. So we see the other extremes, which ones are highest, which ones are the lowest. Make sure that when you look at this question, you may see something where it asks for the strongest, and you may see something that asks for the weakest. The Master in Chemistry has a couple of questions where it asks you to put them in order. And sometimes it asks you for increasing, sometimes it asks you for decreasing. Yes?
Intermolecular refers to like how the molecules react with each other, right?
Between neighbors, yes.
Okay.
Yeah. So intra is between. So it's within a molecule. Inter means between neighbors. Okay? All right, so if we look at the way that we can see these dipole attractions on boiling points and melting points, here's an example of two compounds that have almost the same molar mass. They're right at 30. So therefore, their dispersion forces are going to be approximately similar. So the one on the bottom, ethane is an example of a compound that just has carbon-carbon and carbon-hydrogen bonds. That's the only two types of bonds that are in that molecule. And those are both nonpolar bonds. So there's no dipole in that molecule, so therefore it only has dispersion forces. And if we look at its boiling point, it's a minus 88, and its melting point is 172. But formaldehyde is another combination of compounds that weighs right at 30. But now you've got carbon attached to oxygen, and that produces a permanent dipole, so you've got charge separation. And the other thing, this is not a symmetric molecule. This is an AB3 geometry, so it's trigonal planar. So that means the electron density is all pulling to one side, so it has a permanent dipole. Even though they're similar molar mass, the difference in boiling points is about 70 degrees. And that's simply due to this interaction that's coming from the dipole-dipole interaction that can occur within the formaldehyde and the lack of it with the ethane. Now, typically melting points, because you don't have to break the bonds apart, melting point changes are not as pronounced, and we'll see that with some other examples. Even though this one is pretty significant, Sometimes the melting point changes may only be 30 or 40 degrees, where this one's still pretty large in its size. So this shows a plot of the boiling points for a group of compounds that weigh between 41 and 46. And what varies on them, they're all combinations of carbon, hydrogen, and either have oxygen or nitrogen, and they have different geometries, and those geometries lead to different dipole moments. So the number of debye was the magnitude of the dipole moment. The compound that has the lowest dipole moment, which is propane, the nonpolar compound, has a boiling point of around 225 Kelvin. If we start to introduce a small dipole in it, dimethyl ether, it jumps up 20 or 30 degrees, not a huge jump. But if we start to get a larger and larger dipole moment, become a more and more polar compound, going up to acetonitrile, we start to see that shift jumps up to about 325 or so. But the trend is the stronger that dipole is, the greater the intermolecular forces, the greater the boiling point is. And we see that consistently throughout science. All right, so here's an example where we're going to try to look at a couple of compounds, and we're going to do in set A and set B, and I want us to choose the one that has the highest boiling point. So therefore, we're looking for the thing that has the highest intermolecular forces. Okay, so look at A, the comparison of this guy versus this one. So they're the same empirical formula, so it means that they've got the exact same atoms, just the way they're arranged is different. So if you look at the major difference that we see, this one has the two fluorines opposite or opposed to one another. This one has the two fluorines on the same carbon atom. Okay. What strikes you in terms of, does either of those have a dipole? Which one does? Okay, the right one, fluorine's the most electronegative atom, and that doesn't have symmetry in the molecule. It's definitely going to pull electron density in that direction. Okay, so this side would be electronegative. This side would be electropositive. Okay, what about the one on the right? It's still got the same fluorine atom, so it would be electronegative in this direction and electronegative in this direction. So does that have a permanent dipole then? Say no, why not?
Because they're pulling in opposite directions.
They're symmetric in the opposite directions, exactly right. So these two things, the vectors would cancel each other out. So this one has no dipole moment. So this is a nonpolar compound. And this one would be a polar compound. So the question is, which one's going to have the highest boiling point? The one with the highest dipole moment is going to be the one with the highest one. So that's what we're looking for. We're looking for, does it have a dipole, and is there a symmetry that cancels that dipole out? So the things we're trying to answer. Maybe it's a little clearer on the question on the bottom. So this one is isomers where you have a double bond exists, that in the double bond makes it different, where the single bond, you'll learn this in organic, the molecules can spin around a little bit and they can have some movement or rotation. But when you put that second set of electrons in there, that rotation is restricted and it controls movement. And we'll learn about that as you go more advanced organic classes. So if we look at these two, we've got the two chlorines opposed to each other on opposite sides, but they're both on the bottom. This one on their own opposite sides, one's on bottom and one's on the top. So the one that's on the right is much like what we had on the top left. You've got the dipole moments on each one that are opposing one another, but there's symmetry in the molecule. So that makes that a nonpolar compound, where the one that's on the left, both of them are pointing in the down direction. So it would have a permanent dipole on this side of the molecule. So if we're looking at the one that's going to have, this makes it polar. So this would be the one that's going to have the highest boiling point. Any questions on that? I'm going to ask you a clicker question probably in a minute, either that or at minimum an exam question coming up. You'll have to answer a question like that. You too many. Okay, so when we look at these attractive forces and where they play roles, one of the major ways we see this is the term solubility. So solubility, how much of something will dissolve in a solvent, depends on the attractive forces between the solute, but it also depends on what are the attractive forces between the solvent molecules. And we'll take in our upcoming chapter, in chapter 13, we'll look at that in great detail. Our general rule that we use is like dissolves like. So nonpolar solvents dissolve nonpolar molecules. Polar solvents dissolve polar molecules. And things that have mixed polarities, so that have some portions of the molecule that are polar and some are nonpolar, dissolve compounds like it. Okay, so you try to match up what are the physical properties in terms of polarities of the analyte I need to dissolve with a solvent I might put it in. So things that are miscible, when we say something is a miscible liquid, means that it will dissolve in each other in any proportion or any ratio. It could be 99 parts of one and 1 part of the other. Or it could be 1 part of the other and 99. You could switch them. Any combination you put them together means that they'll mix. That's what a miscible liquid is. If we look at polar substances are going to dissolve in polar solvents. A common way that we classify a polar substance is the presence of a term called hydrophilic groups. So hydro means water, philic means loving, so water loving. And we look for these particular types of functional groups on a molecule, an OH, hydroxide, a CHO, so if we go back and think of structure more detail of those, an OH group, all right, the CHO is going to be C double bond OH, a carbonyl is a C double bond O, look at that in a molecule. A carboxylic acid, and then an NH2 group or chlorine. Those are examples of hydrophilic groups. So those are all going to be, if we see the more of those types of groups that we see on any molecule, the more soluble it's going to be in a polar solvent. Now the opposites are true. When we look at things that are nonpolar, we're looking for nonpolar solvents to dissolve those. So the term that we use to describe nonpolar is hydrophobic. Okay, so water hating is the term that matches that. We primarily look for two things when we describe hydrophobic or nonpolar. These are not the only things, but if we look at classic chemistry that involves carbon and hydrogen, we're looking for carbon-carbon bonds and carbon-hydrogen. If those are the only types of bonds in the molecule, it's always nonpolar. Okay, so that's the types of terms that we look for. So when you have both present, both hydrophobic and hydrophilic parts of the molecule, it becomes a competition between the attraction of the polar groups with water and the attraction of the nonpolar groups for something of their own kind. Who wins out that competition controls the solubility. So not everything is a purely polar molecule or a purely nonpolar molecule. It's got a balance between polarity and nonpolar functional or areas of the molecule. Its solubility, how much dissolves in a particular solvent, is based on that competition between the polar and the nonpolar. So we said what miscible liquids are. Immiscible liquids means that the two solvents do not dissolve in one another. An example is pentane. Pentane is C5H12. So that's only carbon and hydrogen bonds. Carbon-carbon and carbon-hydrogen, so that's a nonpolar molecule, and water we know is a polar molecule. Both are clear liquids. What happens is the attractive forces between the water molecules are much stronger for other water molecules than the pentane. So you mix these two things together, you can shake it as much as you want to try to stir it together, but as soon as you stop the mixing, they instantly separate into two distinct layers. We call that a bilayer. Okay, so they're going to separate on order of their density. So water's being the most dense substance, it's going to fall to the bottom of the beaker. The pentane has a much lower density, it's going to float on top of the water. Okay, so that's an example of an immiscible system. There's no combination, I should say. We'll learn in upcoming chapters that that almost everything will dissolve to a small amount, but the amount of that solubility may be very, very, very small. Okay, so it may be only one particle in a billion. And it may be less than that. So sometimes there's a particle there. It's just not very much of it. All right, the next type of bond that we want to talk, now we've added dispersion bonds, and we've got hydrogen bonds, and something's tickling my nose, so I got to. Makes you trying to sneeze. The next type of intermolecular force, we've had dispersion forces and dipole-dipoles. The next one is the hydrogen bond. So a hydrogen bond only occurs with very unique situations in molecules. It's when you have a small, very electronegative atom bound to a hydrogen atom. And when that happens, what happens is those atoms pull the electrons towards it strongly. And there's only three types of cases where it occurs. It's where you have oxygen connected to a hydrogen, nitrogen connected to a hydrogen, or fluorine connected to a hydrogen. And it's not just the presence of the oxygen, nitrogen, or fluorine. It's got to be connected to the hydrogen. So when those occur, because hydrogen doesn't have any other electrons, remember hydrogen's atomic number one electron. When that one electron is pulled away from its nucleus, it deshields the nucleus and exposes the nucleus that's positively charged. And that deshielding makes it a very strong center of attraction of positive charge, and it attracts electron clouds from neighboring molecules. We call this the hydrogen bond, or H bond. So if we think of it in a space-filling model, whenever we have the hydrogen connected to one of those three, and these are the easy ones to see in the periodic table because they're next to each other in row 2. So 5A, 6A, 7A in row 2, or column 2, period 2 of the periodic table. So oxygen, or nitrogen, oxygen, and fluorine. Those are the only cases that this occurs. So because of this extra attraction where you have this positively charged proton exposed and the electron density going over, this attraction that occurs is stronger than a normal dipole-dipole. And if we think of it in a electrostatic map, these things are always going to line up. It is a type of dipole-dipole, but we call it a super dipole because the strengths are so strong. Okay, so a hydrogen bond is frequently called a super dipole. We talked about some of the unique properties of water. So water has two of these types of bonds. It's got two hydrogens that are connected to an oxygen. So when it has this charge separation, it's actually occurring in multiple places on the molecule. That means that each water molecule can have 3 points of attraction with the neighboring molecules. So each hydrogen connects with a neighboring oxygen, and then each oxygen connects with a hydrogen. So it could have these points going out that allows the water to have a unique characteristics of bonding, and that's what gives water its unique properties. So we talked about one of the things that's unique about water is that when it freezes, its density actually decreases. It's one of the few substances that does that. Why it does that? Because when it goes into the solids phase, these things expand out. They get into a very unique crystal structure that minimizes the distance between these and maximizes that interaction. If we look at something like ethanol, so ethanol is a CH3, CH2, OH, but it's got this OH group. It's got a hydrogen connected to an oxygen. That's one of the requirements for the hydrogen bond. And because of that, it gets this super dipole that's formed. And that hydrogen bond, where you have the charge separation, the positive charges from the exposed nucleus on the proton can interact with the oxygen from a neighboring molecule, and it forms this strong dipole-dipole interaction. So because of that, we have a little bit stronger intermolecular forces, boiling points and melting points, associated with compounds that can hydrogen bond. So when we're trying to choose the largest or the smallest in the list, one of the first things I frequently look for, is there something that can hydrogen bond? So is there one of those combinations where we have hydrogen connected to nitrogen, oxygen, or fluorine? And we try to recognize that. So hydrogen bonds are some of the strongest intermolecular forces that we have. So they have a great influence on the properties. They're stronger than the dipole-dipole or the dispersion forces. Substances that can hydrogen bond are always going to have higher boiling points and higher melting points. compared to things that have similar molar masses that can't interact with these. But even though these are strong forces, they're still much less than the forces that hold molecules together. So the intramolecular forces within molecules. So the hydrogen bonds are only 2 to 5% of the strength of covalent bonds, the bonds between atoms in a molecule. And you think with 2 to 5%, well, it's trivial. Where it becomes significant is how many of those bonds are there. Is there only just one single bond, like with the ethanol, or are there 4 of those, like in the case of repetitive with a water molecule? Then they become more and more significant. So here's an example of how it affects physical properties. So ethanol, and it can create a hydrogen bond. So it has the hydrogen bond with a hydrogen connected to the oxygen on the end. Molar mass is 4607 compared to the dimethyl ether. Exactly the same atoms, they're just arranged in a different way. Now, both of the compounds are polar. So there is a dipole moment in dimethyl ether, and it is a slightly polar compound. But because of the superdipole of the hydrogen bond, even though the molar masses are similar, the change in the boiling points are almost 100 degrees. So 22 degrees for the compound that can't, negative 22 degrees for the boiling point for the thing that can hydrogen bond, where ethanol's boiling point is around 78. Now this is an example where you see the melting points are not near as different. So the melting points are only about 20 degrees difference, but the boiling points are the big change. Because whenever you have to take something into the vapor phase, you completely break that hydrogen bond apart, where it stays in the liquid to solid transition. That hydrogen bond can still exist. Okay, so if we do a comparison to trends in the periodic table, so we're going to look at 2 columns in the periodic table, the things that are in the 4A family and things that are in the 6A family. And these are hydrides, so it means that element surrounded with hydrogens. Now, the graph that's in the textbook is wrong. And it's simply wrong in the naming. So the things that, let me color these right. So the things that are red are the 4A. So those are things that are underneath carbon. So that should go to this line. And the things that are in blue, the 6A group, should go up here with the things that are underneath oxygen. They just got the label switched just a little bit. If we do a comparison of trends that we see, the ones that can do the hydrogen bonds, therefore they have substantially higher boiling points than what we see from the others. So if we look in the, nothing in the 4A family can do a hydrogen bond, but if we look in the 6A family, oxygen can. So when we make these hydride compounds, we're just taking that element and putting the number of hydrogens needed to fulfill the octet. So water would be up here, if we do our scale, water's up here like at this point, so it's at a positive 100 in its boiling point. But as soon as I get rid of that ability to hydrogen bond and go to the next largest thing, H2S, it drops down to about a minus 70 or 80. And as I get subsequent larger and larger in the molecules, what I see is that there's a slight increase, and that increase is with increased dispersion forces. The boiling point and melting points are getting slightly larger and larger. These are boiling points. And I see a similar thing in the 6A family, that was the 6A that we looked at. If I look at the 4A family, I see a very similar trend. These are all going to be nonpolar molecules, and we see as we get larger and larger masses associated with them, the molar masses increase, we see an increase in the trends, and the boiling points go up as well. All right, so let's do another practice one. It says choose the substance that's a liquid at room temperature, and the other phase is a gas in the system. So let's look at the top pair. I've got CH3OH versus CH3CHF2. So it's not a clicker question, where we have to kind of think about what's going on with this. We need to be able to sketch out quickly how the atoms are attached in the molecule. So CH3 is the tetrahedral, and then the OH means that the hydrogen is connected with the oxygen. So what does that one tell me? What type of, that's an H bond. So this is an H bond, so that tells me that there's some strong intermolecular forces. Now what about the other side? Does it have an H bond? So we've got the same thing. We've got a CH3. So the CH3 group, and we've got a carbon with a hydrogen on it, and then there are two fluorines attached to that. All right, so it's not obvious in this particular formula that that's the way the atoms are attached, but I know that hydrogen has to be terminal, and so does fluorine. So that's the way the atoms have to be organized. Now this has fluorine atoms as well. Are those H bonds? Why not?
They're not bonded to the hydrogen.
That's exactly right. So no H bonds, because those fluorines are attached to carbon, not hydrogen. So the question is, of this, which one is going to be the substance that's a liquid at room temperature? It's going to be the one with the highest intermolecular forces. It would be this one, because it can H bond.
Wait, that's the gas. Or,
That's the one that's the liquid.
oh,
So we're choosing the one with the strongest intermolecular forces. So this is the liquid. The other one, this would be the gas phase. Okay. All right. So let's do a similar thing for the pair at the bottom. What do you take on it? So this one has an oxygen. Now, oxygen is an atom we look for in a hydrogen bond. And this one has a nitrogen. That's another atom in a hydrogen bond. But is this oxygen connected to a hydrogen? It's not. It's connected to these neighboring carbons. So no H bond. And if I look over to this one, the hydrogens are terminal, connected to the nitrogen, so that would be an NH2 group. So this one can H bond. So this is the one that's a liquid at room temperature. That's the one. The other one's going to be a gas at room temperature. Okay. So we not only have to look for the presence of that oxygen, nitrogen, or fluorine, but is it actually connected to the hydrogen? Any question on that? Make sense? Yep.
So if there's no H bond, just say there's two examples that had no H bond, is there any cases where it would be a liquid no H bond, or is that just?
Oh, sure. Yeah, just you have to have enough other types of forces. So dispersion forces, dipole can be strong enough easily to get it to be liquid at room temperature. Sure, no problem. In fact, if you take this molecule, and put one more carbon on it, so make it CH3, and make that a 2 there. This one's diethyl ether. It's a liquid at room temperature. And it's a common solvent that we use. The problem is that it's right at the borderline. It's one of the chemicals we have problems with in labs because its boiling point is about 40 degrees. So 40 degrees Celsius. So that's right at 100 degrees Fahrenheit. Normal temperatures in labs are below that. But we had a problem in 1998. The air conditioner went out in the building, and we had problems that the bottles of diethyl ether are just sitting on the countertops and were starting to boil. It's a highly flammable substance, so we had to take all of those solvents, relocate them to another place for the course of the summer, because we literally lost the air conditioning system for 3 months, so they get a new unit in. That was a miserable summer. I wasn't teaching classes then, but I was running a very active research lab. We were getting computer failures constantly, but we were starting to work at 6 and stopping at 2 because it was just so physically hot in the lab. We perspired enough that we didn't want to be around anybody else the rest of the day. Okay, so here's your clicker for this. So we want to arrange them in order of increasing boiling points. So the hand I'll give you is the increasing. The one that's going to be the highest is going to have the strongest intermolecular forces. The one that's going to be the lowest is going to have the weakest. So look at those three structures. Which one? figure out which one's the lowest, which one's the highest on the intermolecular forces. One more. Okay. See how we go. Okay, a little stair step. So 2 of you thought it was A, 3 thought it was B, and 5 of you thought it was choice C. I like choice C. Okay, let's think about the why of that. All right, so if I look at the types of intermolecular forces that I have. So all of them have oxygen, so that means they all have a little bit of a dipole moment. If I look at these 2, they're very similar in that they're going to have this dipole moment and this polarity the same way. The reason that it's smaller with this one is that it's a smaller molar mass. Okay, compared to this molecule, it's got these extra carbons out, so that means it's going to have extra dispersion. Larger molar mass always means more dispersion forces if everything else is equal. The one that makes this one the high is the fact that this is the H bond, so it's the super dipole. That means it's going to be the one that's the highest. So when I looked at the list, this is the one that sticks out to me that's the obvious, the highest one. I take it down to just these choices. So I just have to look at it between those 2. That's the obvious one I see. And then I'll look at the comparison of the other 2. Okay, which one is going to be the smallest of those? And because of the likeness of the molecule, and this one has the extra molar mass, means it's going to have more dispersion forces than the smaller molecule, so that puts that one at the smallest. Okay. If you'll look at the old exams, you'll see examples. I ask a question like similar to this every year, where you have to choose either highest or lowest, or put them in order on the list, and you've got some mastering chemistry problems that are like that. Okay, so 4th type of force, and this one is not exclusively occurring just between molecules that are alike, unlike the ones that we just talked about. This one's the ion dipole force. So it's going to occur whenever we have an ionic compound, and we're going to dissolve that into a polar solvent. So something that has a dipole for the solvent, and it's going to attract the ionic compound. So a classic example of this is whenever you take an ionic substance and you dissolve it in water. So if I look at something like sodium chloride, it's got the negatively charged chloride anion, and it will attract the water molecules, but the water molecules will orient so that the positive portion of the molecule is pointed in towards the negatively charged water, because opposites attract. All right, and if I look at the positively charged cation, the water molecules now orient so that the negative portion of the water molecule is pointed inwards towards the positively charged cation. Still the same solvent, they just flip around so that the charges are opposite when they interact with another. So the strength of this dipole ion attraction or ion dipole attraction is one of the major factors that tell us if something's going to be soluble in water or not. We know that ionic compounds have a strong force between them because you have this opposite charge in the electrostatic interaction. To overcome that, we've got to create all these new attractions that exist between the solvent and the solute for both the cation and the anion in the system. Okay, so if we summarize these 4 types of interactions, the dispersion forces are the weakest of these. They're present in everything, and they tend to get bigger as the size of the molecule gets bigger. Polar molecules have dipole attractive forces between them. Hydrogen bonds are the strongest of the intermolecular forces that we have between pure substances. Again, the ion dipole is not a pure substance. It's a solute-solvent mixture. Hydrogen bonds are present whenever we have the hydrogen connected to one of the 3, oxygen, nitrogen, or fluorine. And the only example we have with HF combination is the molecule of hydrogen fluoride or hydrofluoric acid. So since that's the only combination that can achieve that. The ion dipole attractions are present in mixtures where we have ionic compounds with polar solvents. And the ion dipoles are the strongest of the intermolecular forces. And I'll show you a number comparison on the next page. And those are critical things that control the solubility of ionic compounds in systems. So this is table 11.14 in the textbook, and it just gives you an idea in terms of the magnitude of these different types of forces and how on a relative scale of one another. So dispersion forces are typically with small molecules only a few kilojoules per mole or less. And when you get to a very large molecule, something like the interactions that would occur in a grease molecule. So if you've ever used a grease gun to grease the bearings on anything mechanical, that's a very long hydrocarbon molecule, like a C30. Okay, so 30 carbons in a straight line. So it's a long tube if you want to think of it in space, and those things can line up with one another and have a lot of surface interaction. So there you can have total dispersion forces when that's the only type of energy of 10 to 20 kilojoules per mole, but that's still small. If we think about going back to what we talked about in chapter 9 and 10, we talked about bond energies, single bond energies that we talked about. So we talked about how to use Hess's law to calculate the enthalpy of a reaction, and we could break a bond and form bonds. Single bond energies for like carbon, hydrogen, carbon, carbon, they're in the neighborhood of 500 kilojoules per mole, 400 to 500. So they're still way more than these types of energies that we have. Okay, the dipoles, so when we have a permanent dipole in a polar molecule, they get up a little bit larger. So they can be 3 to 20 plus. The super dipole, they increase by a factor of to 5 to 10 in terms of their magnitude. So now you're about 40 kilojoules per mole. And finally, the largest when the ion dipoles are a little bit larger than that, 30 to 100 kilojoules per mole. But again, all of these are less than the smallest single bond energies that you would have in a covalent bond in a system. Now, again, one of the things we talked about is that's per every one of those interactions. If we look at something like DNA, you all know that you've had this pounded in you for every science class that you've had or biology class. You got a phosphate backbone with a sugar, and it's got the bases on it, and there are 4 different bases that you can have. So the TA forms a pair, and the CG forms a pair. When we start looking at those structures, the adenine-thymine pair forms 2 hydrogen bonds between the neighboring molecules, and the cytosine-guanine pair forms 3 hydrogen bonds between the neighboring molecules. And even though each one of these bond energies as a hydrogen bond is fairly small in terms of maybe only a few to less than 10 kilojoules per mole, when we repeat that a huge number of times, that's what gives DNA its stability. So this repetitive 2 or 3 hydrogen bonds repeats for the strand of DNA. So we'll say on average, if it's only 2, how many base pairs are in a segment of human DNA? So how big is the human genome? Anybody know? We sequenced it in the 1990s. How many base pairs are there? Say again? It's 2.5 billion. So I mean, it's not quite trillions, but there's a lot. Okay, so you take that number and the bond energy per hydrogen bond, and you multiply it by 10 to the 9, and that gives you tremendous stability associated with the DNA molecule. And that's what allows DNA to have this particular strength that it has to be resistant to changes that occur in systems. Whenever it starts to unwind through the molecular machinery, it's so strong and attached to itself, living systems have to build special things to decrease that bonding so that when they separate, you can pull the old strands apart, create a new strand, and the replication of DNA. Now, one of the ways that we can see the properties come to life is with things that we can observe. Surface tension is one of those. So surface tension results when we have a tendency of liquids to try to minimize their surface area. So we'll have The surface area getting smaller when a liquid forms drops, and we see that be spherical in shape as long as there's minor gravity components. And I showed you the water molecule at the start of the chapter, that if you have water in free space, it forms a sphere. We can see something like surface tension, that if you throw something that's lower density on the surface of water, it floats there instead of sinking in, even though that substance has a higher density than that of water itself. What happens is the layer of molecules on the surface have a different behavior than the molecules that are in the interior. And this creates what's called a cohesive force for the surface molecules that have a net pull towards the interior. So the ones on the surface don't have neighbors around them, or as many neighbors around them, so the bond strengths between the few neighbors that they have become stronger. It's almost like a glue that holds the molecules together. So it becomes like an elastic skin, is the terminology the author uses. And you can demonstrate this to yourself by getting a coffee cup and getting a metal paper clip. Even though we know steel has a density, most steel has a density 6.5 to 7, 6 times at least that of water, so that should sink to the bottom. But if you take a pair of tweezers, place it carefully on the cup of water, you can get it to float. So one of the things that I do with small kids is challenge them to give them tweezers and a cup of coffee, see how many they can get afloat in a cup. All right, so if you go carefully, you can easily get 10 plus paper clips to float in a cup. And I think the record was like at 22, somebody did, but they had a bigger than normal coffee cup, I'll say that. All right, but if we can destroy that surface tension, this effect of the surface tension causing that elastic skin disappears. So once I get them to create float, I tell them to get a drop of detergent and put it on the edge of the cup and let it just slowly run in. You watch that drop of detergent, and as soon as it hits the liquid, all of the paper clip falls to the bottom instantly, because that surface tension is broke by the soap. The surface active agents destroys the surface tension on the surface. So we can understand these properties and see them start coming to life. So the surface tension exists because the fewer neighbors means that those molecules are less stable than the ones that are down in the interior. Therefore, they have a higher potential energy and they're harder to displace. So if we look at how surface tension changes depending on how strongly things bond together, something like water that can hydrogen bond, it has a surface tension of about 73 megajoules per square meter at room temperature, and it is temperature dependent, where if you look at something that's not as polar, something like benzene, it's about 3 times less, even though it's a substantially larger molecule. And this is kind of giving you the view of what's happening at the surface versus what's happening at the interior. The interior molecules can have neighbors in all dimensions. The surface ones can only see half of that. So the interactions that are there become stronger in magnitude. The way that you see this, I'm an apple fanatic. I have an apple 2 or 3 times a week with lunch. So either that or a snack at night. You take an apple, and if it's wet from dew in the morning, the water molecules beat up on the surface. So what does that tell me about the surface of the apple? So does that tell me, is the surface polar or nonpolar? It's nonpolar, because the water molecule are trying to get away from it. They're trying to minimize their contact. Therefore, they're all running together and making these little beads. If it were a polar surface, what would happen is the water would spread out evenly on the surface, trying to maximize contact. Okay, so that concept of, are they trying to are they like the neighbors and they're spreading out? Are they trying to all accumulate together to get away from it? That drives these other properties that we see as well. So one of those is viscosity, and viscosity is the resistance of a liquid to flow. So basically, we see viscosities whenever something is a thick, like syrup. The unit of viscosity is a poise, and it depends on the measuring device. We have to have some reference, but it's a gram per centimeter per second. So the more weight you put on it, the more it's going to flow. We usually Our standard unit that we use to get these numbers a little bit more standardized or smaller is a centipoise, and by definition, water at room temperature 25 degrees is 1 centipoise in value. That's how we use to calibrate our instrument. So the larger the intermolecular forces or attractions, that results directly in a higher viscosity. So if we look at things like the straight chain hydrocarbons, so pentane weighs 72. It has a value of around 0.2. Hexane is 86, so every one of these we're adding 14 to it, another CH2 group. It's 0.32. Heptane's 100. It's around 0.4. Octane 114, 0.54, and we just see the trend goes up and up and up. So as we make this chain longer and longer and longer, we see a direct increase with the viscosity, to the point where things will transition from being a liquid at room temperature to being a solid at room temperature. All right, so if you've got something that's a solid at room temperature, and you want to convert it to a liquid, what we do, we apply heat to it. And we take it so the temperature is high enough that we're above its normal boiling point. It converts from our normal melting point from a solid to a liquid state in matter. Okay, another factor that we see is viscosity is always going to be related to the intermolecular forces. So the stronger the intermolecular forces, the higher it's going to be. Now, the previous example that we looked, we just had dispersion forces. But when we start looking at things that have the other types of intermolecular forces, things like shape come into play. So if we've got something that's more spherical in shape, that means it's going to have a lower viscosity, because molecules that are round could roll off of each other easier than ones that have higher surface contact. So things that are long and tubular shape are other types of shapes that you could have. So the less surface contact means the lower the traction you're going to have, the lower dispersion forces that you would have. If we look at what temperature's role is, we mentioned temperature. Raising the temperature increases the kinetic energy of molecules. Therefore, it makes them easier to overcome the intermolecular attractions that you have and allows them to flow. If we just look at water, water undergoes probably one of the most substantial changes that we see in terms of the properties. Even though we don't see viscosity very easily without a measuring device, probably the way that we've seen this more than anything else is you heat your syrup in the microwave. Okay, before you heat the syrup up, you turn the bottle up and you gotta wait for your syrup to slowly come out. You heat your syrup up in the microwave or whatever till a little sticker says hot on it, and then you pour it out and it runs just like water. So water itself is a value of 1 at 20 degrees. If we heat it up to 100, it drops to about a quarter of that value. So it's a 75% reduction in that physical property. That's a big change when you're thinking about things engineering-wise. Okay, so look at these, and this is a group question, so you can ask one another. I'll give you 30 seconds or a little longer to figure it out. So ask one another, figure out which one of these is going to be the most viscous. That's going to be our last question. Y'all can turn around and face each other. Y'all can talk to each other any way you want to do when it's a group question. Yeah. We need to learn how this works too. So you got 30 seconds. So when the clock expires, your answer has to be in. You can always change your vote. If you voted and you don't like what you did, whatever you've matched last is what's going to be entered. Okay. 10 seconds. Five. Everybody's voted. What we got? Okay, 2 major answers. Well, only 2 answers. So everyone thought it was either C or E. So let's figure out what it is. So we ruled out everything but those 2. And some of you thought it was C. and some of you thought it were E. So if we're looking for the most viscous, am I looking for the one with the strongest intermolecular forces or the weakest? Okay, so I'm looking for one with the highest intermolecular forces, IMF. Okay, so this one is only carbon-hydrogen. This is a carbon triple bond, CH, CH3. That one only has carbon-hydrogen bonds. That's a nonpolar molecule. Where this one has two OH groups, so these are our H bonds. It's going to be the one that's the highest. That's going to be the one that's going to be the most viscous. This compound is actually a compound called glycerol. So it's known because of its high viscosity in reagents. All right, so the last example that we're going to cover on this quickly is capillary action. So introduce this because you've got a master chemistry problem with it. Capillary action is the ability of a liquid to flow up a thin tube against the influence of gravity. So you'll find out in the next week or two that I'm a big supporter of blood drives and give you extra credit if you attempt or go give blood at the blood drive at Southeastern next week. If you're going to do that, one of the things we're going to do is check your iron level. Okay, see if you're anemic or not. So they're going to prick your finger and take a hollow tube, and the blood will go up that tube and rise in that tube. And the reason it rises in is the result of capillary action. So there are two forces that are working in conjunction with one another, and those two forces are cohesion and adhesion. Cohesive forces are the forces that hold liquid molecules together. That's how much you like your like substances. Adhesion are the attractive forces between the liquid to the tube's surface. So how much does the liquid like the surface? So the more the adhesive forces, the more the pull of the liquid up the sides of the tubes, and the cohesive forces are pulling the liquids to the interior. And what we see is we make the tubes narrower and narrower. The adhesive forces get larger, greater the cohesive forces, and the amount of liquid that goes into the tube gets higher and higher. So we see the greatest influence of capillary action with the narrowest of tubes. So that's just the pull of the liquid itself that's pulling the liquid in the tube. So the narrower the tube, the higher the liquid's going to rise in it. And we also can look at the surface, and we can learn a lot about the magnitude of those forces by studying the surface of the liquid inside that tube is called the meniscus. And the shape of that meniscus tells us something about the competition between the cohesive and adhesive forces. So with water, the glass is a polar substance. So water is a polar substance, and the meniscus with water is concave because the adhesive forces are strong between the glass and the water. It's higher than the cohesive forces for water molecules for itself. So the water is actually trying to climb up the walls of the glass. Okay, so the shape of the meniscus is down. If we look at the opposite tube, it has mercury in it. So with mercury, it's convex instead of concave because now the cohesive forces are the strongest, the forces between the mercury molecules themselves. So they're trying to stick with themselves more than the glass. So the surface, the meniscus inverts and goes the other way. So we can learn by simply putting a substance inside of a glass tube and looking at the shape. Is it a polar or non-polar substance? If it's polar, it's going to be concave. If it's non-polar, it's going to be convex in its shape. Okay, so that's the point where we're going to stop at on those. I don't know why that won't save. We're going to have to solve that problem in a second. Okay, so what we're going to do is spend the next few minutes talking about some end of the chapter problems. So I'll do these again probably towards the end of next week. This chapter is a little messed up because of the losing Monday. So 38 says, describe the kinds of intermolecular forces present in each element or compound. All right, so the first one is this pH 3. So if I look at pH 3, I need to know something about the electronegativity. To know, is that going to have a dipole or not? And I've got to know something about where the electron densities are. So if I look at phosphorus, phosphorus is going to be like nitrogen. So phosphorus has 2 lone pairs to it, and each hydrogen has 1. So when it forms a structure, it's going to have a single bond, much like NH3 would have. Okay, so if I look at what is this, it's an AB3E. So the shape that it would have would be trigonal pyramidal. So it's got a lone pair of electrons up here at the top. And then if I look at the differences in electronegativity, see if I manage to put that on the next page or two. Didn't. Okay, so 4, 3.5, 3. I'm thinking that the difference between the phosphorus is somewhere in the neighborhood of 2.6, 2.7. Hydrogen is 2.1 electronegativity. So that means that there's a pull in electronegativity in the inward direction on these. And that results in there being a net moment in the up direction, so away from the hydrogens. So that means that it's a slightly polar compound. So it's not symmetric, so that means it's going to have dispersion forces. Everything's got dispersion forces. So dispersion forces plus dipole. All right, if we look at HBr, so if we go down and look at B, HBr, hydrogen is 2.1. The bromine is a couple of down, so it's probably around 2.8. It's going to be very similar. It's hydrogen connected to a halogen, but that halogen is not fluorine, so it's not an H bond. It's just going to be in fact, it's the same one. So it's dispersion plus dipole. And we do those types of comparisons to see what types of bonds are present in each one compared to what is geometry. If we look at, just do one that's different, do D. So I2 was a single bond with 3 lone pairs around it, but it's bound to itself. So regardless of what the electronegativity is, the fact that it's binding to self means that it's a nonpolar molecule. So the fact that it means it's nonpolar molecules only have dispersion. So dispersion forces only. Okay? So that's what we're trying to answer with that. So arrange the compounds in order of increasing boiling point and think about your reasoning why. Okay, so these are all compounds that are in the 6A family. And it's got oxygen, sulfur, and selenium are the things that vary. So the oxygen, sulfur, and selenium. So there's something special about one of them. What is it? The water can hydrogen bond. So because of the hydrogen bonding, water's on this end. So the highest, it's the greatest. So if I compare the next 2 compounds, which one would be the smallest of the 2? Why sulfur? It's a smaller molar mass, exactly right. So they're all in the same family, going up and down. So once you get beyond what the hydrogen bonding can be, they go in order of the molar mass. All right? For each pair, pick the one with the higher boiling point and explain your region. So I've got the first pair, we'll do 2 of them. So the first pair is NH3. It's an AB3E, okay, versus methane, and it's an AB4. Okay. What can you tell me about characteristics of either of these? Intermolecular forces. Polar, nonpolar. Anything you tell me? Okay. So this is polar. So it's got a dipole, so it has dipoles. Is there anything special about its dipole? It's hydrogen bond because the nitrogen's connected to hydrogen. So it H bonds. Okay. What about this guy? Okay, it's symmetric. Okay, the bonds are all the same. So it's nonpolar. So the only thing that it have is the dispersion forces. So dispersion only. Okay, so the types of intermolecular forces that they're going to have are going to be much weaker. So the question is, choose the compound with a higher boiling point. Definitely going to be an H3. Okay, so let's look at the bottom one. CO2 versus N2O. So really to answer this one, we have to go back and we have to do some Lewis structures. So I'm going to quickly draw some Lewis structures out. So carbon has got 4 electrons, valence electrons. Oxygen has 6, but there's 2 oxygen atoms. That's 12. That means I've got 16 electrons to put around the structure. Okay, so do a single bond to each. So that uses 4. That leaves me with 12. So I put the remaining 12 around the exterior atoms. So does everything have an octet there? It doesn't, so I have to collapse a lone pair end from each one of the exterior atoms, result in the structure that we have with CO2. CO2. Got 2 lone pairs on each oxygen, 2 double bonds, 1 to each one of the oxygens from the carbon. Okay, so now I've got that. That's an AB2. AB2 is linear, so even though there's a dipole between each one of these, carbon to oxygen, the fact that it's symmetric and they're in line with one another, they cancel out. So this means that it's nonpolar and dispersion only. Okay, compared to the other molecule. So if we look at what we've got with the NO2, so nitrogen is in the 5 family. The oxygen is the same thing. There's 6 of those times 2. So now we just got an extra electron in here, and it takes it to 17. Okay. The result in this one with this extra electron, if we work out the geometry, is that this extra electron sitting out here somewhere, and it works as a partial electron pair. Okay, so it results in a bent geometry rather than a linear geometry, and that causes this to be a polar molecule. Okay, so the one that's polar has a dipole moment, so it can have dipole interactions. One that can have dipole interactions is going to have the highest boiling point associated with it. Sometimes they're obvious. Sometimes you actually have to work through a Lewis structure to answer those things. Okay, so what are the types of intermolecular forces in each one? Okay, so the simple ones are the things that are monoatomic. What type of intermolecular forces can happen with monoatomics? Only dispersion. Yeah, so those guys are only dispersion forces. All right, then you've got to start looking at molecule to molecule. Okay, what about this guy? What type of intermolecular? Everything has dispersion, so dispersion is true of every one of these. So, but this one is dispersion only. So, but all these others have dispersions as well. So this one's dispersion plus. What else can HF have? Okay, and the H bond is a dipole dipole interaction, so the H bond covers that. All right, if we look at this guy, so the silicon has four lone electrons around it. Each one of the hydrogens would form a bond. So the result would make it 4 single bonds, so that becomes an AB4. So that's a tetrahedron. So with a tetrahedral shape, they're all the same. So the result is this is a nonpolar molecule. If it's nonpolar, it's only dispersions. Okay, so that's how we're answering those types of questions. All right, so what's the wrong direction? So choose the one with the higher vapor pressure. And vapor pressure is the next topic that's in our notes, but some of our questions deal with vapor pressures. The thing I'll tell you, there is a question on vapor pressure that we haven't talked about yet, but I've already worked a sample problem with that. And it involves the size of a room of a certain size, and you have to calculate what is the density of the gas in that room. But I've worked an example out just like that. You're just going to have to plug in what your gas is and what the dimensions are of your room. But you can see the exact sample the way that I did that. Okay, vapor pressure is whenever you have a liquid that's in a closed container and some of that liquid emits off into the gas phase. All right, and it creates a gas. So what is the pressure that results from that transition at a given temperature? So how much pressure is produced from the gas? So the pressure of the gas. Okay, so that's what vapor pressure is a measure of. So what we look at with vapor pressure is that the higher the vapor pressure results from lower intermolecular forces. So the less something wants to stick together, the more easily it will go to the gas phase. So things that have higher intermolecular forces have low vapor pressure. Things that have low intermolecular forces have high vapor pressure. So we're looking for the one that is the higher vapor pressure, therefore the lowest intermolecular forces. If we look at this first pair, and I'm just going to do one of these for our comparison, they both have carbon with 4 things attached. One has 4 hydrogens, the other one has 3 hydrogens and a chlorine. So because this one's symmetric, it's equivalent all the way around, that means it's a nonpolar molecule. Right? And it's going to have low intermolecular forces. This one has a dipole moment because of the lack of symmetry with it. So that makes this one have it's polar. It's got a dipole-dipole interaction. So the one that's going to be the lowest intermolecular forces, it's going to be this guy. It's going to have the highest vapor pressure. Okay? If I do a similar comparison, just quickly look at the next pair. Both of them have the OH group that can hydrogen bond, but the difference, this one has a CH3, this one has 3 carbons with the hydrogens around them. So the difference is this portion of the molecule, right? This gives you more dispersion forces. More dispersion forces, there's more intermolecular forces. So the one that's going to be the lowest of the two is that one. That's the comparison you have to make. Last one, you have to draw out Lewis structures to figure out a strategy to get there. All right, so next one is looking at decide would something dissolve in another? Would it be a homogeneous solution or would it be heterogeneous? We have to look at what are the types of intermolecular forces in both of the solvents and decide would they be miscible or not. So this one is carbon, hydrogen, and carbon-carbon bonds, and that's present in both of them. So they're only dispersing forces. That means that they would mix. They're similar. They're both nonpolars. All right, and nonpolar and nonpolar would mix. So it would be a homogeneous solution from those forces that were involved. All right, if I look at one where that's not the case. So if I look at the one at the bottom, this has a hydrogen bond. Okay, so that's a dipole-dipole. That's going to result in a polar molecule. This is nothing but the dispersion forces. So this is a nonpolar molecule. Hydrophobic for nonpolar, hydrophilic for polar. The two things would be immiscible or be a heterogeneous solution. So those two things would not mix together in one phase. They'd form a biphase layer. So we're out of time at that point. If you need help on these, go find the tutors, come by my office hours, get the help that you need. Okay? All right, with that, we're going to call it quits, and I'll see you in the lab tomorrow.